going to do those together. Those are infinite sequences and series. So I want us to think about this sequence. We've got 1, 1/2, 1/3, 1/4, 1/5, and so on. So that would continue. That sequence is neither arithmetic nor geometric because you're not adding something each time, and you're not multiplying by something each time. All right. You are adding a number to the denominator, but that's not equivalent to adding a set number to the value. So you're not adding or multiplying. So if we were going to write a formula for this, if we were writing an a sub n formula, how could we write that formula? Let me do this. Let's make this n, right? This would be the first term, second term, third term, fourth term, fifth term. So for the first term, we've got 1. For the second term, we've got 1/2. For the third term, we've got 1/3. Fourth term, we've got 1/4. So would this formula work? 1/n. Right, just 1 over the number the term is. Okay, so what we're going to be looking at here for these infinite sequences and series is infinite. We're going to be looking at what happens as the numbers get bigger and bigger and bigger and bigger. All right, so as n approaches infinity, so for 6, 7, 8, 9, 10, a million, a gazillion, what happens to the value of a sub n? Okay, it's going to go down. That's true. So does it ever become negative? It does not. What value does it get closer and closer and closer and closer to? 0, right? Because each fraction, as you increase that denominator, it's going to get closer and closer and closer and closer and closer to 0. So as n approaches infinity, a sub n approaches 0. Now, we are going to introduce some notation here called limit notation. Limits, although this chapter 15 is called limits, chapter 12 is not, but we're going to introduce the limits here. Limits are the building blocks of calculus. So if you take calculus next year, we always begin with limits. So you already understand a little bit of that going into that class. So limits look at what happens as a number gets closer and closer and closer to a value. So to write this with limit notation, we would write it like this. We would say the limit as n approaches infinity. So we've got that LIM as our limit. Underneath it, we'll put n arrow infinity. That means n approaches infinity. And then here we'll put of a sub n. And that value equals 0. Okay? So that's what our notation looks like. It reads the limit as n approaches infinity of a sub n equals 0. Okay? So let's consider these limits right here. I'll let you copy those down. first one. We've got now the limit as n approaches infinity of 1 over n squared. What is going to happen is that n gets bigger and bigger and bigger. What does the value approach? Still 0, right? In fact, it will approach 0 even more quickly than 1 over n, because you would have 1 over 1 squared, which is 1. You have 1 over 2 squared, which is 1/4. 1 over 3 squared, which is 1/9. So those numbers in the denominator are going to get larger more quickly for this case. So the limit as n approaches infinity of 1 over n squared is 0. What about 2? What's going to happen with 2? As n increases. Okay? It's still going to get smaller, right? Even though our numerator is a large number, we have 200,000 in the numerator, as n gets bigger, that number is going to decrease. So let's use our calculator here just to kind of look at this. If we've got a formula, I'll clear this out. Let's see, 1, 2, 3. Get rid of one of those. Okay. 200,000 divided by, I might have to put an x instead of an n. If we look at our table, mine's starting at 16 because it's where it showed up. We can see the value is decreasing, but this right here doesn't tell us much. I'm going to go to my table set, and let's start at 0. Let's change this amount that goes up by to 1,000. So we can see a little bit better. There's an error at 0 because we can't divide by 0, but then we see our numbers decreasing here, still decreasing. Are they ever going to be negative? Will they get below 1? When will they get below 1? Whenever we get over 200,000. So if we were to go back, let's just start at 200,000. That's 20,000, isn't it? Here's 1. Here they continue to decrease. All right, what is this going to approach? Eventually, it's going to get close to 0, right? It can't ever be negative because you're not introducing a negative number there. As those numbers get larger and larger and larger, this still approaches 0. It takes it a lot longer to get there than 1 over n, right? But it still approaches 0. So no matter what your numerator is, if it's any number, even if we had, 500 billion in the numerator, eventually 500 billion over n approaches 0. Okay? So there are several properties of limits that we need to know. And I'm going to let you write those down first, and then we'll talk about what they mean. Now let's talk about what some of these mean. Okay, so the limit as n approaches infinity of 1 over n to the r power. So a variable really to any power, it could be x squared, it could be x to the fifth, it could be x to the millionth, is going to equal 0 because that denominator will get larger and larger and larger and larger. The only exception is that the r cannot be negative. The r has to be positive here. Because what happens if I have a negative r? What if I have like 1 over n to the negative 2? How do I rewrite that without a negative exponent? we have to move it to the top. So it would be just really like n squared. So it wouldn't have a denominator anymore. And that number is just going to get larger and larger and larger. So as long as you have a positive exponent here, even if it's a small, like it could be n to the 1/2 x, or it could be, it could be n to the 1/2 or n to the 1/10 or something. As long as it's positive, this denominator will get larger and larger and larger. The limit will approach 0. Now there are some other properties of limits that we can use to help us out. If I have the limit as n approaches infinity of one series, which is a sub n, plus or minus another series that's b sub n, I could split those up and take the limits of them separately and then add or subtract those together. So I can split it with the plus or minus sign. If I have a limit that is a sub n times b sub n, I can also take the limits of each one of those series separately, sequences separately, and then multiply those together. If I have the limit of a sub n over b sub n, that's division. You can take the limit of the top, limit of the bottom, and then divide the two. Okay, so we can separate for all of those. The last one we have here, if I have the limit as n approaches infinity of c, and c is a constant, so to think of an example with numbers, that would be the limit as n approaches infinity of 5. 5 is always 5. There's no variable to change there, so the answer to that would be 5. Okay, so if you have a constant, it just stays the same because there's no variable that is changing there. There's no n in your problem. Okay, so all of these properties are properties we are going to use to help us find the limits of equations. Okay, so here is an example, and I wrote it like this because your textbook writes it like this. You won't see it written like this very often. But we're supposed to find the limit as n approaches infinity of a sub n if a sub n equals 9/5, 16/4, 65 over 27, and then it puts ... 7n squared plus 2 over 2n squared plus 3n. This part, this is telling you how they got their rule, right? So the first term, it was 7 times 1 squared plus 2, which gives you 9, and 2 times 1 squared plus 3 times 1, which is 5, right? They're telling you how they got the rule for the series each time. The likelihood that you're going to come up with this right here, if they don't give it to you, is very low. So really, the only thing that you need to worry about here is this part. So what it's asking for is really for you to find the limit as n approaches infinity of 7n squared plus 2 over 2n squared plus 3n. Now this is a little more complicated than just looking at 1 over n, or even 200,000 over n, because 1 over n, we can kind of think of what the numbers are, 1/5, 1/10, 1/100th, 1/1,000,000th, and think, well, that's fractions getting smaller, it approaches 0. Plugging numbers into this is not going to be easy. So I'm going to teach you another method that you can use, and it uses those properties of exponents that we have, or properties of limits that we have. So the first step that we are going to do for these problems is divide every term by the highest degree term from